Welcome to the Deep Dive. Today we're tackling, well, a bit of a giant, Amazon Web Services, AWS.
Yeah, it's huge. We've got a whole load of material here, basically covering everything from the foundational stuff right up to some pretty advanced services they offer.
Exactly. Sources covering things like EC2 compute, IAM for identity, serverless, data analytics, security, the works.
It's a broad landscape for sure.
So our mission today, cut through all that, we want to give you the crucial info, a clear picture of AWS without drowning you in tech speak.
Think of it as the AWS Essentials Tour. Get you grounded.
Okay, so where did this whole AWS thing even come from? It feels like it's always been here.
Well, what's interesting is Amazon actually started building it for themselves internally way back in 2002.
Solving their own problems first.
Exactly. They realized their infrastructure was a strength. Then, 2004, they sort of tested the waters publicly with SQS, the simple queue service.
Okay.
But the big launch, the one people really remember, was 2006. Relaunched SQS, plus S3 storage, and EC2 compute. That was the start of AWS as we kind of know it.
And then Europe in 2007. It grew fast.
It really did. And the scale now, I mean, the sources mention $90 billion in annual revenue for 2023.
Wow. $90 billion?
Yeah,
that's massive.
it really underscores just how much of the internet, how many businesses rely on AWS now.
Yeah.
It's fundamental infrastructure for so many.
Okay, so if you, our listener, want to start building on AWS, where's ground zero?
It absolutely has to start with regions and availability zones. That's the physical foundation.
Regions and AZs. Break that down for us.
All right, think of a region as a large geographic area like UNIS East or maybe Western Europe.
Okay, like a country or part of a continent.
Pretty much.
Right.
And then within each region, you have multiple availability zones or AZs. And these are they're physically separate data centers.
Physically separate. So different buildings.
Yep. Independent power, cooling, physical security, the whole setup. But they're linked together with really fast, low latency network connections.
Why the separation then?
It's all about resilience, high availability. If one AZ has, say, a power outage or some other issue, your applications running in the other AZs in that same region should keep ticking along.
Redundancy, built-in backup locations almost.
Exactly. You spread your apps and data across multiple AZ to tolerate failures.
So where do the actual AWS services we use, like EC2, fit into this? Are they regional, zonal?
Good question. Most of the core services you interact with are region scoped. Our info points this out. EC2 virtual machines, that's IaaS.
Infrastructure as a service.
Right. Elastic Beanstalk, the Pay on NAS platform,
Yeah.
Lambda for serverless functions, FAL-yes, even things like recognition for image analysis, a SaaS offering, they all operate within a specific region you choose.
So if I launch a virtual server, an EC2 instance in, say, Ireland,
Right.
it lives in the Ireland region.
Precisely. And it will run within one of the specific availability zones within that Ireland region. If you wanted resources in Frankfurt, you'd have to specifically deploy them there.
Okay. And there's a list somewhere showing what's available where.
Yeah. The sources mention a link to the AWS Global Infrastructure Region table. It shows all the regions and the services in each one.
Got it. Regions and AZs, the physical where. Now, how do we control who can actually do things with these resources? Security's got to be paramount.
Absolutely. And that's where AWS Identity and Access Management, or IAM, comes in. It's the central control plane for all your AWS permissions.
IAM. Okay, what are the main parts of that?
You've got a few core concepts. First, users. These usually map to actual people.
Like me or someone on my team.
Exactly. Then you have groups, which are just collections of these users. Makes managing permissions easier.
Okay.
The permissions themselves are defined in policies. These are JSON documents, basically rule books saying who can do what to which resources.
So a policy might say this group can start and stop EC2 instances.
Precisely. And finally, you have roles. These are a bit different. They're meant to be assumed by like an EC2 instance itself or another AWS service so it can interact with other services on your behalf.
So my web server might assume a role to read files from S3 storage.
That's a perfect example. It avoids hard coding credentials.
Makes sense. So how do these actual users log in and use AWS?
Three main ways. There's the AWS Management Console, the web interface.
Yeah.
You log in with a password, and crucially, MFA, multi-factor authentication.
That extra code from your phone or key fob.
Yep, super important. Then for automation or scripting, you've got the command line interface, the CLI, and the software developer kits, SDKs. Both of those use access keys.
Access keys, tell me more. Need to be careful with those, I assume.
Extremely careful. They're long-term credentials for programmatic access. You generate them per user. You get an access key ID, kind of like a username, and a secret access key, which is like the password.
And that secret access key, keep it secret.
Absolutely. Treat it like your most sensitive password. Don't share it. Don't embed it in code. Don't email it. Keep it locked down.
Any examples of what they look like, just so people recognize them?
Yeah, the material gives a fake one. An ID might be something like AKEASK4E37PV498-3D6C, and the secret key could be like AZPN3's was WCNDHB0NA229A1 DZBZ05FQKAZQ. Long random strings. Point is, guard that secret key.
Got it. Keep it secret, keep it safe. What about the MFA options? You mentioned key fobs.
Right. AWS supports several types. You can use virtual MFA apps on your phone, but also physical hardware key fobs. Gemalto makes some common ones. And for the more regulated AWS GovCloud regions, there are specific ones from SurePassID.
Okay. Physical tokens for extra security. You also mentioned IAM roles again for services. How does that work in practice? Why is it better than access keys on an EC2 instance?
Well, think about that EC2 instance needing to read from S3. The old way might have been to put an access key file on the instance. Big security risk if that instance gets compromised.
Right, the keys could leak.
Exactly. With IAM roles, you create a role, attach the S3 read policy to it, and then associate that role with the EC2 instance when you launch it. The instance then automatically gets temporary credentials from AWS to perform those S3 actions. No long-term keys stored on the instance itself.
Ah, much cleaner. Temporary managed credentials.
Much more secure. It's the recommended best practice.
Okay, so wrapping up IAM, what are the absolute must-do best practices? The non-negotiables.
All right, key takeaways for IAM. First, don't use your root account for daily tasks. Lock it down, use MFA, and only use it for specific account-level things.
Create separate IAM users instead.
Yes, one physical user per IAM user. Put those users into groups. Apply permissions to the groups, not the individual users, makes management way easier.
Okay.
Enforce strong passwords and absolutely enforce MFA for all users. Use roles for AWS services needing permissions, like we just discussed. Use access keys only for CLI SDK access and protect them.
And review permissions regularly.
Definitely. Use the IAM Credentials Report and Access Advisor to see who has what access and when they last used it, clean up unused permissions, and finally, never ever share IAM users or access keys. One person, one identity.
Solid advice. IAM is clearly critical. Okay, let's get some compute power. EC2 Elastic Compute Cloud. That's the workhorse, right?
Absolutely. EC2 is one of the oldest and most fundamental AWS services. It's infrastructure as a service. Essentially, you're renting virtual machines in the cloud.
So instead of buying physical servers, racking them, powering them, I just rent virtual ones from AWS.
That's the core idea. And it's not just the virtual machines, EC2 instances. It includes virtual disk storage, EBS volumes, load balancing traffic across instances, ELB, and automatically scaling the number of instances up or down, auto-scaling groups, ASG.
Okay. Virtual servers running my code, but how do I control network access? Who can talk to these servers?
That's where security groups come in. They're fundamental. Think of them as a virtual firewall attached to each EC2 instance.
A firewall for each server.
Exactly. It controls what inbound traffic is allowed to the instance and what outbound traffic is allowed from the instance. You define rules based on ports and IP addresses.
So like allowing web traffic on port 80 or 443?
Precisely. Security groups operate at the instance level and they're stateful.
Stateful? What does that mean?
It means if you allow inbound traffic in on a certain port, say port 80 for HTTP, the return traffic going out for that specific connection is automatically allowed, regardless of your outbound rules. The security group remembers the connection.
Okay. So I don't need to explicitly allow the web server's replies back out.
Correct. And crucially, security groups are default deny. You have to explicitly allow the traffic you want. You can allow traffic from specific IP ranges or even from other security groups.
What are some common ports we need to know when setting these up?
Yeah, there are a few classics. Port 22 is for SSH Secure Shell, how you usually connect to Linux instances remotely.
Right.
Port 21 is for FTP, though less common now. Port 22 is also used for SFTP, which is Secure File Transfer over SSH. Much better than FTP.
Okay, SSH and SFTP on 22. What about web?
Port 80 for HTTP, unencrypted web traffic, and port 443 for HTTPS, secure web traffic.
And for Windows?
Port 3389 is for RDP Remote Desktop Protocol. That's how you typically get a graphical desktop on a Windows server.
Okay, so I open the ports I need. How do I actually connect SSH for Linux?
Yep. From a Linux or Mac terminal, you'd use the swish command with your private key file and the instance's public IP or DNS name. Our notes mention you can even set up shortcuts in your .config file. For Windows, you might use a tool like PuTTY for SSH.
And for RDP to Windows instances?
You'd use a remote desktop client pointed at the instance's public IP or DNS and use the username and password often one AWS generates initially that you retrieve.
Got it. Now, what about these EC2 dedicated hosts? Sounds different from standard instances.
It is. A dedicated host is a physical server, the actual hardware that's dedicated entirely to your use. No other AWS customers share that physical box.
Why would I need that? Isn't the point of cloud shared infrastructure?
Primarily for two reasons: compliance and licensing. Some regulatory standards might mandate single-tenant hardware, and some software licenses, maybe older ones, are tied to physical cores or sockets. Dedicated hosts let you bring those licenses to AWS, called Bring Your Own License, or BYO.
Ah, okay. So for specific regulatory needs or funky licensing, how do you pay for them?
You can pay on demand by the second, just like regular instances, but it's more expensive. Or you can get reserved dedicated hosts for a 1 or 3 year term for a discount. But yeah, generally dedicated hosts are the priciest EC2 option.
Good to know. Now, controlling where my instances run within an AZ, placement groups.
Yes. Placement groups give you more control over the physical placement of your instances relative to each other. 3 types.
Okay.
First, cluster placement groups. These pack your instances close together within a single AZ. The goal is lowest possible network latency and highest throughput between instances. Think 10 GBPs for high-performance computing. Downside: if that rack or AZ has an issue, all your instances might be impacted together.
Okay, speed over individual fault isolation. What's next?
Spread placement groups. These do the opposite. They ensure each instance runs on distinct underlying hardware, maximum of 7 instances per group per AZ. Greatly reduces the risk of simultaneous failure due to hardware issues. You can even span a spread group across multiple AZs for even higher availability.
So spread is for maximizing fault tolerance. And the third?
Partition placement groups. These spread instances across different logical partitions, where each partition represents a set of racks within an AZ, each with its own network and power source. These can scale to hundreds of instances and are ideal for large distributed systems like Hadoop, Cassandra, Kafka, where you want fault isolation between groups of instances, but still potentially good locality within a partition.
Cluster for speed, spread for isolation, partition for large-scale distributed apps. Got it. Now, instance lifecycle stopping versus terminating versus hibernating.
Right. Stopping an instance is like shutting down your computer. The instance OS shuts down, you stop paying for the compute time, but the attached EBS root volume, your main disk, persists. You can start again later.
And terminating.
Terminating is permanent deletion. The instance is shut down and deleted. By default, the attached EBS root volume is also deleted, though you can configure it to persist. Any data on instance store volumes, temporary local disks, is always lost.
Okay, stop is temporary, terminate is final. What about hibernating?
Hibernation is interesting. It's like putting your laptop to sleep. It saves the contents of the instance's RAM to the EBS root volume and then shuts the instance down.
So when you start it again?
It resumes exactly where it left off, with all the applications and memory state restored. Can really speed up startup for apps that take a long time to initialize or warm up caches. But there are limitations: instance families, OS, size, and you can't hibernate for more than 60 days.
Cool option for specific cases. Okay, we mentioned EBS volumes for storage. Let's dig into instance storage a bit more. EBS is persistent, right?
Correct. EBS, Elastic Block Store, provides network-attached block storage volumes. Think of them like virtual hard drives in the cloud. They persist independently of the EC2 instance's life.
And you attach them to one instance at a time within the same AZ?
Exactly. One instance attachment at a time, and both the instance and the NDS volume must be in the same availability zone. Because they're persistent, you can detach a volume from one instance and attach it to another in the same AZ, keeping all your data.
That's key for data survival if an instance fails. What about backups?
You create EBS snapshots. These are point-in-time backups of your EBS volume stored durably in Amazon S3.
Do I need to detach the volume to take a snapshot?
It's recommended for guaranteed consistency, especially for database volumes, but often not strictly necessary for, say, root volumes. Snapshots are incremental. Only the changed blocks since the last snapshot are saved, which is efficient. And a huge benefit: you can copy snapshots across AZs or even to different AWS regions.
Copying to other regions, great for disaster recovery.
Absolutely essential DR strategy.
Now, EBS is one-to-one instance attachment. What if multiple instances need to access the same shared file system, like for a WordPress site's uploads folder?
That's where Amazon EFS, Elastic File System, comes in. EFS provides a managed, scalable networked file system. Multiple EC2 instances, even across different AZs within the same region, can mount and access the same EFS file system concurrently.
So it's like a shared network drive.
Exactly. It uses the standard NFSv 4.1 protocol. Perfect for content management systems like WordPress or Drupal, web serving, data sharing, any scenario where multiple Linux instances need shared file access.
Linux only.
Primarily designed for and compatible with Linux AMIs. Access is controlled via standard security groups. Data can be encrypted at rest using KMS. It's POSIX compliant, scales automatically, and you pay for the storage you actually use.
So for my multi-instance WordPress site, EFS is the answer for the shared media library.
That's the classic use case.
Yeah.
EFS for shared files, EBS for the instance's OS and local data.
Okay, that clarifies the storage options. Now let's talk high availability and scaling, making sure our app stays up and handles traffic, load balancers, and auto-scaling.
Crucial concepts. Elastic load balancing, ELB, is the starting point.
Yeah.
It automatically distributes incoming application traffic across multiple EC2 instances.
So no single instance gets overwhelmed.
Right. And if one instance fails a health check, the ELB stops sending traffic to it, routing requests to the healthy ones, improves availability and fault tolerance dramatically.
Like a smart traffic cop for my servers, what types of load balancers are there?
3 main types. The old one is the classic load balancer, probably avoid for new stuff. Then there's the application load balancer, ALB.
LB.
Yeah, operates at layer 7, the HTTPS layer. It's really flexible. Can route traffic based on the path in the URL, host name, headers. Perfect for microservices, containers, routing to multiple applications on the same set of instances. Supports HTTP2, WebSockets, redirects. It's the workhorse for web apps.
Okay, ALB for web stuff. What's the third?
Network Load Balancer, NLB, operates at layer 4 TCP UDP. It's designed for extreme performance, ultra-low latency. Think gaming, financial trading platforms, high-throughput TCP applications. A key feature is it provides a static IP address per AZ.
So ALB for most web apps, NLB for high-performance TCP static IP needs. What are target groups?
With ALBs, you don't point the load balancer directly at instances. You point it at target groups. A target group is just a collection of your back-end resources, usually EC2 instances, but could be IP addresses or Lambda functions. The ALB routes traffic to the target group, and the target group manages the health checks for the individual targets within it.
Gotcha. Separation of concerns. What about handling multiple SSL certificates on one load balancer if I host several websites?
That's where SNI comes in, server name indication. It's an extension to the SSL TLS protocol that allows the client, the browser, to tell the server, the load balancer, which host name it's trying to reach during the initial handshake.
So the ALB can look at that requested host name and present the correct SSL certificate for that specific site.
Exactly. Allows you to host multiple secure sites behind a single ALB using different certificates. Very useful.
Okay, load balancers spread the traffic. How do we automatically adjust the number of servers based on that traffic?
That's auto-scaling groups, or ASGs. An ASG lets you define a desired number of EC2 instances, a minimum size and a maximum size. It then automatically launches or terminates instances to maintain that desired number.
But how does it know when to scale?
Through scaling policies. You can configure policies based on metrics like average CPU utilization across the group, network traffic, maybe the number of requests hitting your ALB, or even custom metrics from CloudWatch.
So if CPU goes over 70%, launch a new instance. If it drops below 30%, terminate one.
Precisely. That's called target tracking scaling. There are other types too, like step scaling based on CloudWatch alarms, or even scheduled scaling to anticipate predictable traffic patterns. ASGs also perform health checks and automatically replace unhealthy instances.
So ASGs handle both scaling and self-healing. Very powerful. Does this scaling apply to databases too?
Yes, managed databases often have scaling features. Take Amazon Aurora, the relational database service. It uses Aurora replicas, read-only copies of your main database.
For handling read traffic.
Exactly. And you can configure Aurora auto-scaling to automatically add or remove these read replicas based on metrics like CPU usage or the number of connections. You can even create custom endpoints to direct specific types of queries, like analytics, to a dedicated pool of replicas.
What about Aurora Serverless? Sounds even more hands-off.
It is. Aurora Serverless automatically starts up, shuts down, and scales the database compute capacity based on your application's actual needs. It's great for infrequent, intermittent, or unpredictable workloads because you don't pre-provision capacity. You just pay per second when it's active.
Pay-per-use database scaling. Interesting. What if things go wrong? How do we restore RDS or Aurora databases?
You can restore from automated backups or manual snapshots. It always creates a new database instance with the restored data.
Okay, restore creates a new DB.
You can also sometimes use native database tools. For MySQL MariaDB on RDS, you can use MySQL dump, save the backup to S3, and restore it to a new RDS instance. For Aurora MySQL, you can use Percona Extra Backup to back up to S3 and restore to a new Aurora cluster.
Lots of connections hitting these potentially scaling databases. Connection pooling.
Good point. That's where Amazon RDS Proxy comes in. It's a fully managed database proxy that sits between your application and your RDS or Aurora database.
What does it do?
It pools and shares database connections, which reduces the memory and CPU overhead on your database for managing thousands of connections. It also makes your application more resilient to database failovers. The proxy maintains connections while the underlying database fails over, reducing downtime. It's serverless, scales automatically, and supports MySQL and PostgreSQL compatible engines.
So RDS Proxy handles connection management and improves failover. Okay, that covers scaling compute and databases. Now, how do users find our amazing scalable application, DNS Route 53?
Exactly. Amazon Route 53 is AWS's managed DNS service. DNS, domain name system, is basically the phone book of the internet. It translates human-friendly domain names like www.google.com into the IP addresses computers actually use, like 172.2unshivs.160.142.
Can't live without it. So Route 53 manages those translations for my domain.
Yes. It's an authoritative DNS service, meaning it holds the official records for your domain. It's highly available, scalable, fully managed, and even comes with a 100% availability SLA. The 53 in the name comes from the standard DNS network port.
Okay, need some DNS terminology. Domain Registrar Records Zones.
Right. A domain registrar is where you buy your domain name. Route 53 can be one. DNS records are the actual entries mapping names to IPs or other info, like AAA, CNAME, MX records. A zone file contains all records for a domain. Name servers answer DNS queries. Authoritative ones hold the master records. You have top-level domains, TLDs like .com, second-level domains, SLDs like Amazon and Amazon.com, and subdomains like Oz and Oz.Amazon.com. The full name is the FQDN.
Okay, that helps. How does a typical DNS lookup work when I click a URL?
Quickly, your browser asks your local DNS server, from your ISP maybe. If it doesn't know, it asks a root DNS server. The root points it to the TLD server for e.g. for .com. The TLD server points it to the authoritative name server for the SLD, e.g. Amazon.com servers, maybe Route 53. That server gives the final IP address back. Your local server caches it based on the TTL value and gives it to your browser.
All happens in milliseconds usually.
Hopefully.
So Route 53 holds my records. What types can I create?
The main ones are A records, hostname to IPv4, AAA records, hostname to IPv6, CNAME records, alias from one hostname to another, and NS records delegates a zone to specific name servers. There are many others for email, MX, text, TXT, etc. Each record has a name, type, value, TTL, time to live for caching, and crucially, a routing policy.
Routing policies. That sounds powerful. What can they do?
They control how Route 53 answers queries. Simple policy just returns the value in the record. Weighted lets you send percentages of traffic to different endpoints.
Yeah.
80% to server A, 20% to server B. Latency-based routes users to the AWS region with the lowest latency for them.
How smart. So users in Europe get routed to a European server.
If you set it up that way, yes. Failover policy lets you set a primary and secondary endpoint. If the primary fails a health check, traffic goes to the secondary. Geolocation routes based on the user's geographic location, e.g. UK users go here, French users go there. Geoproximity is similar, but uses geographic distance and bias, requires traffic flow feature. Multi-value answer returns multiple IPs, and the client picks one randomly, good for client-side load balancing.
Wow, lots of control over traffic flow. You mentioned health checks.
Yes, Route 53 health checks are key. You configure them to monitor an endpoint, IP address, domain name, even CloudWatch alarms. They check health regularly.
And then use that status in the routing policies.
Exactly. Like in the failover policy, if the primary endpoint fails its health check, Route 53 automatically directs traffic to the secondary. You can even combine multiple health checks into a parent health check using and/or logic, or require a certain number to pass.
So I could say, failover only if 2 out of 3 web servers are unhealthy.
Precisely. Gives you fine-grained control over failover behavior.
Can I register my domain name directly with Route 53?
Yes, Route 53 acts as a domain registrar as well as a DNS service. You can manage everything in one place.
What if I registered my domain somewhere else, like GoDaddy, but want to use Route 53's advanced DNS features?
Totally possible. The domain registrar and the DNS service don't have to be the same entity. You'd create a hosted zone for your domain in Route 53. Route 53 gives you a set of name server NS records. You then log into your registrar, GoDaddy, and update your domain's NS records to point to the ones Route 53 gave you.
Ah, so I tell the registrar, hey, Route 53 is now handling the DNS lookups for this domain.
Exactly. After that propagates, Route 53 becomes authoritative for your domain's DNS.
Okay, Route 53 is clearly powerful for directing traffic. Now, let's tie some of this together. The Classic Solutions Architecture section seems perfect for seeing how these pieces fit in real examples.
Yeah, this is where it gets practical. Seeing how you evolve an architecture from simple to complex using different services. We'll look at a basic whatisthetime.com, then a stateful e-commerce site, myclothes.com, and finally mywordpress.com to see how things like shared storage fit in.
Perfect. Let's start with whatisthetime.com. How does that evolve?
You might start super simple. One EC2 instance in a public subnet. DNS points straight to its IP. It serves the time. Done.
But single point of failure, limited capacity.
Exactly. Problems waiting to happen. So, step one, add more instances.
Yeah.
Maybe put them behind a DNS record with multiple IP addresses, though that's basic load balancing.
Yeah.
Better, add an elastic load balancer, ELB.
Okay, ELB distributes traffic to multiple instances. Health checks, too.
Yep. ELB checks instance health, routes only to healthy ones. But all instances might still be in one availability zone. What if that AZ fails?
Ah, right. Need multi-ZA.
Correct. Deploy your instances across multiple AZs within the region. Put the ELB across those AZs too. Now you have redundancy at the AZ level.
Getting better. What about scaling automatically?
Add an auto-scaling group, ASG, that spans those multiple AZs. Configure scaling policies, based on CPU. Now it scales up and down automatically and replaces failed instances across AZs.
That's looking pretty robust. What about cost for this baseline capacity?
If you know you'll always need, say, at least 2 instances running, you can use reserved instances for those to save money compared to on-demand pricing.
Good tip. What's ELB stickiness? When is that needed?
Stickiness, or session affinity, makes the load balancer try to send requests from the same user session to the same backend instance. Useful if the application stores session data locally on that specific instance.
But doesn't that kind of defeat the purpose of load balancing sometimes? What if one server gets all the sticky users?
It can, yeah. It can lead to uneven load distribution. Modern best practice is often to design stateless applications where any instance can handle any request, maybe storing session data centrally in a cache or database. Avoid stickiness if you can.
Makes sense. Okay, moving to myclothes.com, a stateful e-commerce app. How does state change things? Shopping carts, logins?
Right. You need to track user state. A very basic way is using browser cookies to store maybe the cart contents.
But cookies have limits, right? Size, security.
Exactly. They get big, can be tampered with, limited capacity, like 4 KB. Not great for complex state.
So what's a better pattern for myclothes.com?
Typically a 3-tier architecture. Tier 1, load balancer. Tier 2, web app tier EC2 instances in an ASG handling the application logic. Tier 3, database tier, probably Amazon RDS for storing user accounts, products, orders.
And where does the session state live?
Often managed in the web app tier.
Right.
Maybe stored temporarily in memory on the instances, which complicates things if an instance fails or you scale down. Or, much better, stored centrally.
Centrally, like in the database or something faster.
You could store it in the database, but that adds load. A common solution is to introduce a caching layer using Amazon Elasticache, managed Redis, or Memcached, accessible by all instances in the web app tier. Sessions are stored in fast cache.
Ah, so the app checks the cache first for session data. Much faster than hitting the database every time.
Precisely. Improves performance, reduces database load, and crucially, configure your security groups properly between tiers. Load balancer talks to web app tier talks to database and cache tiers, but maybe the database tier can't talk directly back out to the internet. Leaves privilege.
Good security practice. Okay, now mywordpress.com. What's the key challenge there in a multi-AZ setup?
Shared files. WordPress uploads images, themes, plugins. If you have multiple WordPress EC2 instances behind a load balancer for high availability, they all need access to the same set of files.
Can't store them on each instance's local EBS volume? They'd get out of sync.
Exactly. That's where Amazon EFS comes in again. You create an EFS file system and all your WordPress instances mount it. Upload a file via one instance, all other instances see it immediately.
So EFS for shared media plugin storage. What about the WordPress database?
Definitely use a managed multi-AZ database like Amazon Aurora. Gives you high availability for the database itself, plus you can add Aurora read replicas easily to handle lots of website visitors reading blog posts, offloading the main database writer instance.
So WordPress pattern, ELOB EC2 instances in ASG across AZ-SEFS for shared files, Aurora multi-AZ database with read replicas.
That's a solid, scalable WordPress architecture on AWS.
Okay, launching all this EC2, EBS, RDS configuring software sounds like it could take time and be error-prone if done manually. How do we speed up instantiation?
Several techniques. Golden AMIs. Pre-baked machine images with your OS and common software already installed. Bootstrapping, running scripts automatically on first launch to configure things. Configuration management tools like Chef, Puppet, Ansible automate setup and ongoing management. And containerization with Docker packages, everything up for faster, consistent deployments.
Automation is key. What about AWS Elastic Beanstalk? Is that related?
Yes, Elastic Beanstalk is a higher-level service, a platform as a service base. You just upload your application code, Java, .NET, PHP, Node.js, Python, Ruby, Go, Docker. And Beanstalk handles provisioning the underlying infrastructure, EC2, ELB, ASG, maybe even RDS.
It abstracts away the instance and scaling management.
Largely, yes. It simplifies deployment significantly, especially for standard web applications. It has concepts like web server environments for handling HTTP requests and worker environments for background tasks, often using SQS queues. Great for getting started quickly, or if you don't want to manage the infrastructure details yourself.
Okay, Beanstalk for easier deployment. This architecture stuff is really helpful. Now let's talk object storage. S3, simple storage service, feels like it's used everywhere.
It pretty much is. S3 is massively scalable, durable object storage. You store files, called objects, in containers called buckets. Bucket names have to be globally unique.
Globally unique across all AWS users.
Yep. And while buckets are created in a specific region, the namespace is global. You use S3 for tons of things.
Yeah.
Backups, disaster recovery, archives, hosting static websites, media hosting, data lakes for big data analytics, software distribution, the list goes on. NASDAQ uses it for archiving, Cisco for analytics. It's incredibly versatile.
Okay, storing objects in buckets. How do we control access? Who can read or write?
Several ways. Bucket policies are JSON policies attached directly to a bucket, controlling access at the bucket level. Good for things like making a website bucket publicly readable. Then you have IAM policies attached to users, groups, or roles, granting permissions to perform S3 actions on specific buckets or objects. And IAM roles allow EC2 instances or other services to access S3 without needing explicit credentials.
Bucket policies for bucket level, IAM policies for user role level. Makes sense. You mentioned hosting static websites directly from S3.
Yep. You enable the static website hosting feature on a bucket, upload your HTML, CSS, JS files, and make the objects publicly readable, usually via a bucket policy. S3 gives you a specific website endpoint URL, very cost-effective for simple sites. If you get a 403 forbidden error, it's often the bucket policy missing public read access.
Good tip. Now, S3 storage classes. Standard, IA, Glacier. What's the difference?
It's all about balancing cost, access frequency, and retrieval speed. S3 standard is the default. High durability, availability, performance for frequently accessed data. Costs the most per GB stored. Then you have infrequent access IA tiers, S3 standard IA and S3 one zone IA. Lower storage cost, but you pay a fee per GB retrieved. Good for data you don't access often, but need quickly when you do. One zone IA is cheaper still, but only stored in one AZ, so less resilient.
So trade-off. Lower storage costs for IA, but pay for retrieval.
Exactly. S3 Intelligent Tiering tries to automate this. It monitors your access patterns and automatically moves objects between frequent and infrequent tiers, and even archive tiers, to optimize cost. Has a small monitoring fee.
That sounds useful. What about really long-term cheap storage? Archive.
And that's the Glacier family. S3 Glacier Instant Retrieval. Archive cost, but millisecond retrieval, like IA. S3 Glacier Flexible Retrieval. Much cheaper storage. Retrieval takes minutes to hours. You can choose expedited, standard, or bulk. S3 Glacier Deep Archive. The absolute cheapest storage, but retrieval takes 12-48 hours. For data you rarely, if ever, expect to retrieve.
Wow, a whole spectrum. How do I automate moving data between these? Like move old logs to Glacier?
S3 Lifecycle Rules. You define rules based on object age or version. For example, after 90 days in standard, move objects to standard IA. After 180 days in standard IA, move them to Glacier Deep Archive. After 7 years, expire, delete them.
Set and forget based on policy. Does this work for all tiers?
Mostly. The rules transition between standard IA intelligent tiering and into the Glacier tiers. They don't apply within Glacier or for one zone IA.
How do I know what rules to set? How often is my data accessed?
S3 storage class analysis can help. It monitors access patterns on your buckets or prefixes and gives you recommendations on potential lifecycle rules based on observed usage. Takes a day or two to get the first analysis.
Okay. What if I want to share a large data set in S3, but make the downloader pay for the transfer costs?
Enable requester pays on the bucket. Normally, the bucket owner pays for storage and egress. With requester pays, the authenticated AWS user making the download request pays the data transfer fees. Good for sharing public datasets without footing a potentially huge egress bill. Requester must be authenticated, though.
Useful. What about speeding up uploads to S3, especially from far away?
S3 transfer acceleration. It uses the CloudFront Edge network. Your upload goes to the nearest edge location first, then over AWS's optimized network backbone to your bucket's region. Can be much faster for long-distance uploads.
Using the CDM for uploads? Cool. What about really large files, like terabytes?
Use S3 multi-part upload. It breaks the large file into smaller parts, uploads them in parallel, and reassembles them in S3. Faster, more resilient, only need to retry failed parts, and required for objects over 5 GB anyway. For downloads, S3 supports byte range fetches, letting you download specific parts of a file, potentially in parallel too.
Essential for big files. What if I need to do something to millions of existing objects, like change their tags or copy them?
S3 batch operations. You provide a list of objects from an inventory report or a CSV and specify an action. Copy, change tags, modify ACLs, restore from Glacier, even invoke a Lambda function on each object. Massively parallel and managed.
Instead of writing a script to loop through everything myself? Powerful. What about modifying data as it's being downloaded without changing the stored object?
That's S3 Object Lambda. You attach a Lambda function to an S3 access point. When someone requests an object through that access point, S3 invokes your Lambda function first. The function gets the object, can modify it, for example, redact sensitive data, resize an image, convert format, and returns the modified data to the requester. The original object in S3 remains unchanged.
Whoa, dynamic transformation on the fly. Clever. How do S3 access points help with managing permissions?
They simplify access management for shared buckets. Instead of one potentially massive, complex bucket policy, you can create multiple access points for a bucket. Each access point has its own access policy, tailored for a specific application or use case, maybe restricted to a certain prefix, folder, or network origin, like a specific VPC. Granular control without messing with the main bucket policy.
Makes managing permissions easier at scale. How do I get an overview of all my S3 usage, costs, security across my whole organization?
AWS Storage Lens. It provides organization-wide visibility into your object storage. Dashboards showing usage trends, activity metrics, cost optimization recommendations, data protection best practices checks. Really useful for understanding your S3 footprint. Includes metrics on performance, activity, status codes, etc.
High-level visibility. Good. Any gotchas with encryption? I saw a note about SSC KMS limits.
Yeah, if you use server-side encryption with KMS managed keys, SSE KMS heavily, remember that every upload calls generated data key and download calls decrypt makes an API call to KMS. KMS has request rate limits per region per account. For very high throughput S3 workloads using SSC KMS, you might hit those limits and get throttled. Something to monitor.
Okay, potential KMS bottleneck at extreme scale. What about web apps on different domains accessing S3 content? CRS.
Cross-origin resource sharing. If your website JavaScript running on www.my-app.com tries to fetch data directly from your S3 bucket mydata.s3.amazonos.com, the browser will block it by default due to the same origin policy security restriction.
So how do I allow it?
You configure a CORS policy on the S3 bucket itself. You specify which origins, like www.my-app.com, which HTTP methods, GTAT, etc., and which headers are allowed for cross-origin requests. You can allow all origins, but be careful with that. It's fundamental for SPAs or web front ends interacting directly with S3.
Okay. Need to explicitly allow cross-domain access on the bucket. What about temporary access to an object, like a download link that expires?
S3 pre-signed URLs. You generate a URL for a specific object, specifying an action, PDT or PUT, and an expiration time. Anyone with that URL can perform that action until it expires. The permissions are based on the user role who generated the URL. Great for granting temporary, limited access without sharing credentials. Console limits expire to 12 hours, CLIS DK up to 7 days.
Very handy. Okay, let's try to summarize S3. Key characteristics.
Key value object store. Hugely scalable, durable, available. Max object size 5 TB. Versioning support. multiple storage tiers for cost optimization, rich feature set, lifecycle rules, batch operations, object lambda, access points, strong security and encryption, supports static website hosting, performance features like multi-part upload and transfer acceleration, event notifications for automation, and S3 Select for querying data within objects using SQL. It's a foundational service.
Definitely foundational. Now, delivering that S3 content or other web content fast globally, CDNs, CloudFront.
Right. Amazon CloudFront is AWS's content delivery network. It caches your content, static files like images, CSS, JS, videos, but also dynamic content to some extent, at edge locations around the world, physically closer to your users.
So users get faster load times because the data travels a shorter distance.
Exactly. Request hits the nearest edge location. If the content is cached there, boom, served immediately. If not, a cache miss, CloudFront fetches it from your origin server, like S3 or an EC2 instance ALB, serves it to the user, and caches it at the edge for next time.
How do I set up my S3 bucket or web server as a CloudFront origin?
You create a CloudFront distribution and configure the origin. If it's S3, you can make the bucket public or use Origin Access Control, OAC, which is better. It keeps the bucket private and only allows CloudFront itself to access the objects.
OAC sounds more secure. What if the origin is an EC2 instance or an ALB?
The origin address, ALB DNS name or EC2 public IP DNS, needs to be reachable by CloudFront. The EC2 instances themselves can be in private subnets as long as the ALB is public. Or if EC2 is the origin directly, you need to allow CloudFront's IP ranges in the security group.
Can I restrict which countries can access my CloudFront content?
Yes, using geo-restriction. You can create an allow list, only these countries, or a block list, block these countries, uses a geo-IP database. Good for enforcing licensing or copyright restrictions.
What about CloudFront costs? Does it vary by region?
Yes, pricing is based mainly on data transfer out from the edge locations, and the cost per GB varies significantly by geographic region. Some are more expensive than others.
So how can I control that cost if I don't need the absolute best performance in every single country?
CloudFront price classes. You can choose. Price class all, uses all edge locations, best performance, potentially highest cost. Price class 200 uses most locations but excludes the most expensive ones. Or price class 100 uses only the least expensive regions, mainly North America and Europe. Choosing a lower price class reduces cost, but might increase latency for users in the excluded regions.
Trade-off between cost and global reach performance. What if I update a file on my origin? How do I force CloudFront to refresh its cache?
You perform a cache invalidation. By default, CloudFront caches objects based on their TTL, time to live. If you need to update the cache before the TTL expires, you create an invalidation request for specific paths, like imageslogo.png, or for everything. CloudFront then removes the old object from its edge caches, forcing it to fetch the new version from the origin on the next request.
Essential for pushing out updates quickly. Now, what's AWS Global Accelerator? Sounds similar to CloudFront, but different.
It is different. CloudFront is primarily about caching content at the edge. Global Accelerator is about improving availability and performance by optimizing the network path for user traffic to your application endpoints running in AWS regions.
How does it do that?
It gives you two static IP addresses that act as a fixed entry point for your application, advertised from multiple AWS edge locations. User traffic hits the nearest edge location and is then routed over the optimized, congestion-controlled AWS global network to the healthiest application endpoint, ALB, NLB, EC2, in the nearest optimal AWS region you've configured.
So it finds the best network route through AWS's backbone to my application. Less about caching, more about routing.
Exactly. It helps reduce latency and jitter and improves fault tolerance by quickly rerouting traffic if an endpoint or even an entire region becomes unhealthy. Great for global applications needing consistent performance and high availability.
Okay, CloudFront for edge caching, Global Accelerator for optimized network routing. Good distinction. Now, besides S3, EBS, EFS, what other storage extras does AWS offer?
Quite a few specialized ones. AWS Backup provides centralized, automated backup management across many AWS services. Amazon FSx for Windows File Server gives you a fully managed native Windows file system, SMB protocol. Amazon FSx for Lustre is a high-performance parallel file system for HPC, ML, media workloads, often backed by S3.
Okay.
AWS Storage Gateway connects your on-premises environment to AWS Storage. It has different modes. File Gateway, NFS SMB access to S3 FSx, Volume Gateway, ISCSI block storage backed by S3 EBS snapshots, and Tape Gateway, virtual tape library, and S3 Glacier.
Hybrid cloud storage bridge.
Yep. AWS Transfer Family offers managed SFTP, FTPS, FTP servers that integrate directly with S3 or EFS for secure file transfers. AWS Data Sync accelerates and automates data movement between on-prem storage and AWS, or between AWS storage services. And the AWS Snow family, Snow Cone, Snowball, Snowmobile, provides physical devices for shipping huge amounts of data into or out of AWS when network transfer isn't feasible.
Wow, a specific tool for almost every storage need. Okay, let's talk integration and messaging. How do different parts of my application talk to each other asynchronously? SNS, SQS.
Key services for decoupling applications. Amazon SNS, Simple Notification Service, is a publish-subscribe messaging service. You publish a message to an SNS topic, and SNS delivers it to all subscribed endpoints.
What kind of endpoints?
HTTPS URLs, email addresses, SMS text messages, SEOs queues, Lambda functions, mobile push notifications. Very flexible. It's push-based, high-throughput broadcasting.
How's security handle?
Through IAM policies, who can publish subscribe, and SNS access policies, like S3 bucket policies, allowing cross-account access or letting services like S3 publish to a topic.
What's this SNS plus SQS fan-out pattern?
Very common and powerful. You publish one message to an SNS topic. Multiple SQS queues subscribe to that topic. SNS then delivers a copy of the message to each subscribed queue independently.
So one event triggers processing in several different ways simultaneously?
Exactly. Highly decoupled. If one consumer fails, the others aren't affected. SQS provides the durability messages wait in the queue until processed. Just need to make sure the SQS queue policy allows SNS to write to it. Works cross-region too.
So SNS broadcasts, SQS queues. What's the core difference with SQS?
Amazon SQS, Simple Queue Service, is a fully managed message queue. It's primarily for decoupling application components. One component sends a message to the queue, another component, the consumer, pulls the queue, retrieves the message, processes it, and then deletes it. It's pull-based from the consumer side.
Okay. Any different types of SQS queues?
Two main types. Standard queues offer at least once delivery and best effort ordering. Messages might occasionally be delivered more than once or slightly out of order, so your consumer needs to be idempotent. FIFO queues, first in, first out, guarantee exactly once processing and preserve the strict order of messages. FIFO queues have lower throughput limits than standard queues.
What happens if a message repeatedly fails processing?
You configure a dead letter queue, DLQ. After a message fails processing a configured number of times, the max receives count, SQS automatically moves it to the associated DLQ. You can then inspect the DLQ later to figure out why those messages failed without blocking the main queue.
Essential for troubleshooting. What about Amazon EventBridge? Sounds similar again.
EventBridge, which evolved from CloudWatch Events, is a serverless event bus. It's designed for building event-driven architectures at scale. It routes events between AWS services, your own applications, and even integrated SaaS partner applications.
How is it different from SNS SQS?
Think of EventBridge as a central router for events across your whole system. Services emit events to the bus. For example, EC2, instant state change, S3 object creation, custom application event. You define rules on the bus that filter events based on their content and route matching events to specific targets, Lambda, SQS, SNS, step functions, many others. It reacts in near real time and facilitates much more complex event routing and filtering logic than simple SNS topics.
So EventBridge for routing system-wide events based on content rules.
That's a good way to think about it.
And for streaming data. High volume, continuous flow, Kinesis.
Yes, Amazon Kinesis is the platform for real-time data streams. Kinesis Data Streams is for ingesting and storing large streams of data records. It's scalable, durable, consumers pull data from shards, offers ordering within a shard. Data expires after a configurable retention period, default 24 hours up to a year, has provisioned or on-demand capacity modes.
Okay.
Kinesis Data Firehose is a fully managed service to easily load streaming data into destinations like S3, Redshift, OpenSearch, Splunk, etc. It can buffer data, compress it, encrypt it, and even transform it on the fly using Lambda before delivery. No need to manage consumers directly for simple delivery pipelines.
ETL for streams.
Pretty much. And Kinesis Data Analytics lets you run real-time analytics on data in Kinesis Data Streams or Firehose using standard SQL or Apache Flink applications.
So Kinesis for continuous streams, SNS SQS for discrete messages, EventBridge for event routing. What's Amazon MQ?
Amazon MQ is different. It's a managed message broker service for protocols like ActiveMQ and RabbitMQ. If you have existing applications using standard protocols like AMQP, MQTT, JMS, StonePay, and you want to migrate them to AWS without rewriting the messaging parts, MQ provides a managed broker that speaks those protocols. Good for lift and shift or hybrid scenarios.
For compatibility with existing open source brokers and protocols. Okay, that clarifies the messaging landscape. Let's switch to containers, Docker on AWS. Where do I store my Docker images?
You can use public registries like Docker Hub, but for private images, Amazon ECR, Elastic Container Registry, is the way to go. It's a managed Docker registry, tightly integrated with other AWS services like ECS and EKS. They also now have ECR Public for sharing public images.
And how to run those containers, ECS?
Amazon ECS, Elastic Container Service, is AWS's fully managed container orchestration service. It supports Docker containers. You define your application as tasks, one or more containers running together, and run them as services, maintaining a desired count of tasks.
Where do the tasks actually run on EC2 instances?
You have two choices called launch types. EC2 launch type means your tasks run on a cluster of EC2 instances that you manage. You're responsible for patching the OS, etc., though ECS helps. Fargate launch type is serverless. You just define the task resources, CPU memory, and AWS runs it for you without you managing any underlying instances.
Fargate sounds simpler.
It often is, especially for stateless applications, less operational overhead. Key ECS concepts are the cluster, logical grouping, tasks, services, task definitions, the blueprint for a task, specifying images, resources, networking, and the ECS agent runs on EC2 instances and EC2 launch type. Integrates with ECR, CloudWatch logs, IAM roles for task permissions.
How does load balancing work with ECS?
Integrates seamlessly. Application Load Balancer, ALB, is usually the best choice, routing traffic to tasks spread across your cluster based on ports defined in the task definition. Network Load Balancer, NLB, can be used for high throughput UDP. Classic is supported, but not recommended for new apps.
Can ECS automatically scale the number of tasks?
Yes. ECS service auto-scaling. You can scale based on CPU or memory utilization of the tasks, the request count hitting an associated ALB, or custom CloudWatch metrics. Uses target tracking, step scaling, or scheduled scaling policies.
Okay, ECS is the AWS native orchestrator. What's EKS? Kubernetes.
Amazon EKS, Elastic Kubernetes Service, is the managed Kubernetes offering on AWS. Kubernetes is the popular open-source container orchestrator. EKS provides a managed Kubernetes control plane, and you run your worker nodes either on EC2 instances or using Fargate.
Why choose EKS over ECS?
Often comes down to existing investment or preference. If your team already knows and uses Kubernetes, maybe on-prem or in another cloud, EKS provides that familiar experience on AWS. It's more aligned with the broader Kubernetes ecosystem and potentially offers more portability across clouds. Best practice is usually one EKS cluster per region. Use CloudWatch Container Insights for monitoring.
So ECS for AWS native integration, EKS for managed Kubernetes. What's AWS App Runner?
App Runner is even simpler. It's designed for quickly deploying containerized web apps and APIs. You point it at your source code repo or container image in ECR, and App Runner builds, deploys, scales, load balances, and provides HTTPS automatically. Very developer-focused, minimal infra management.
A spectrum from full control, EC6 on EC2, to highly managed Fargate App Runner. Good options. Let's go fully serverless now. Lambda is the core, but what does serverless really mean here?
It means you, the developer, don't manage servers. You write code, functions usually, and the cloud provider, AWS, runs it for you, automatically scaling it based on demand. You pay only when it runs. Well, Lambda is the classic example, function as a service, phase. Other services like API Gateway, DynamoDB, S3 for static hosting. Step functions are also considered serverless because you don't manage the underlying infra.
So with Lambda, I just upload code in Python, Java, Node.js.
Yep, go C#, Ruby 2. Or package it as a container image using Lambda container images. AWS handles provisioning, scaling, patching the execution environment. You pay per request and per millisecond of execution time based on allocated memory.
What triggers a Lambda function?
Lots of things. API gateway requests, S3 object uploads, deletions, messages arriving in an SQS queue or Kinesis stream, SNS notifications, changes in a DynamoDB table via streams, CloudWatch events, EventBridge schedules or events, CloudFront requests, Lambda at edge. Huge integration potential.
Give me a couple of simple serverless examples.
Classic one. S3 triggers Lambda for thumbnail generation. Upload an image to S3, it triggers a Lambda function that reads the image, creates thumbnails, saves them back to S3. Another, serverless CR and job. Use EventBridge to schedule a Lambda function to run every night to clean up old database records or generate a report.
Event-driven and pay-per-use. What about Lambda pricing? Free tier.
Yes, there's a perpetual free tier. 1 million free requests per month and 400,000 gigaseconds of compute time per month. Beyond that, you pay per request and per GB second of compute duration. Can be very cost-effective for many workloads.
What's Lambda concurrency? Limits?
Concurrency is how many instances of your function are running simultaneously. AWS scales this automatically. There's a default account limit per region, shared across all your functions. You can set reserved concurrency for a specific function to guarantee its capacity and isolate it. And provision concurrency keeps a certain number of instances warm and ready to respond instantly, reducing cold starts for latency-sensitive apps, but costs extra.
Cold starts, that initial delay. Any improvements there?
Yes, Lambda Snap Start, currently for Java, Python, and .NET runtimes. When enabled, Lambda initializes your function once, takes a snapshot of the initialized state, and then resumes from that snapshot for subsequent invocations after periods of inactivity. Can dramatically reduce cold start times, making functions much faster to respond initially.
Very useful for user-facing functions. What about running code at the edge, nearer to users?
Right. Customization at the edge, primarily using CloudFront functions or Lambda at edge attached to your CloudFront distribution. Executes code closer to the user, reducing latency.
CloudFront functions versus Lambda at edge, what's the difference?
CloudFront functions are lightweight, run inside CloudFront, use JavaScript only. Super fast startup, subums, very high scale, limited resources, runtime, memory, packet size, can't make network calls or access request body easily. Triggered on viewer request response, cheaper, generous free tier, good for simple header manipulation, URL rewrites, basic auth checks.
Okay, simple and fast. Lambda at edge.
Lambda at edge uses full Lambda functions, Node.js Python. More compute power, longer runtime, larger packages, can access request body, make network calls. Triggered on viewer request response and origin request response, more flexible for complex logic like advanced routing, complex auth, dynamic content assembly at the edge. New free tier, charged like regular Lambda, plus a per request fee.
Choose based on complexity and performance needs. How do we build the actual APIs for these serverless backends? API Gateway.
Yes, API Gateway is the managed service for creating, deploying, securing, and monitoring APIs. Acts as the front door. It can trigger Lambda functions, forward requests to EC2 containers, or even call other AWS services directly. Two main types: REST APIs, feature-rich, traditional, and HTTP APIs, newer, simpler, lower cost, optimized for serverless Lambda backends.
Okay. What about the serverless database, DynamoDB?
Amazon DynamoDB is the go-to fully managed NoSQL key value and document database, designed for high-scale, single-digit millisecond latency, automatically scales storage and throughput. Highly available, perfect fit for many serverless applications.
NoSQL. Different from relational SQL databases.
Yep. Flexible schema, items rows identified by a primary key, stores key value pairs or JSON-like documents. Two capacity modes. Provision, you set read-write capacity units, can use auto-scaling, or on-demand, paper request, scales automatically, often great for serverless.
What if I need even faster reads from DynamoDB microseconds?
DynamoDB Accelerator, or DAX. It's a fully managed in-memory cache specifically for DynamoDB. Sits in front of your table, transparently caches reads, drastically reduces read latency for hot data without changing your application code.
Need my DynamoDB data available globally. Multi-region?
DynamoDB Global Tables. You define your table in multiple regions. DynamoDB automatically replicates data between them, multi-master. Provide low latency local reads writes in each region, and high availability disaster recovery.
Can I automatically delete old items like expired sessions?
Yes, using DynamoDB Time to Live, TTL. You designate a timestamp attribute on your items. DynamoDB automatically deletes items when that timestamp expires. Great for cleaning up old data, managing sessions, compliance, free feature.
Backups for DynamoDB.
Two main options. Point-in-time recovery, PITR. Continuous backups allows restore to any second within the last 35 days. On-demand backups. Full manual backups for long-term retention. Both restore to a new table. Can integrate with AWS backup for centralized management and cross-region copies.
Can I get data out of DynamoDB easily? For analytics in S3, maybe?
Yes. You can export table data directly to S3, or use services like AWS Glue or Data Pipeline for more complex ETL. Once data is in S3, you can query it with Amazon Athena using SQL.
Okay, let's put it together. Simple serverless CRU'd API.
Client makes requests, be example, POC users, to API Gateway endpoint. API Gateway route triggers a specific Lambda function. Lambda function parses the request, interacts with DynamoDB, inserts the new user item, gets a result. Lambda returns result to API Gateway. API Gateway returns response to client. Get, put, delete works similarly with different RUTs functions.
Clean separation. What other key features does API Gateway offer for this?
Lambda integration, obviously. WebSocket support for real-time apps, API versioning, V1, V2. Stage environments, dev, prod, security.authentication, cognito, IAM, authorization, IAM custom Lambda authorizers, API keys and usage plans for throttle and quota management, open API Swagger import-export, request response transformation and validation, client SDK generation, response caching.
Comprehensive. Can you sketch a full serverless website example, like a blog?
Sure, iblog.com. Static files, HTML, CSS, JS, hosted in S3, delivered via CloudFront CDN. Dynamic API calls, comments, posts, go to API Gateway. API Gateway triggers Lambda functions. Lambda functions read, write blog posts, comments, user data in DynamoDB. User logins handled by Cognito. Welcome emails sent via SES, simple email service. Image uploads go to S3, trigger another Lambda for thumbnail generation, fully serverless, scales automatically, pay for usage.
Brilliant example. What about that software updates offloading scenario? How is that serverless thinking?
Original setup might be EC2 serving update files. Huge traffic spike on release day hammers EC2, costs $1 a model. Serverless approach. Put update files in S3, cheap storage. Put CloudFront in front of S3. CloudFront caches the files at the edge globally.
So users download from the nearest CloudFront edge cache.
Exactly. Vast majority of traffic hits CloudFront, not S3 or the original EC2. CloudFront scales automatically, reduces origin load, lowers cost, improves download speed for users. Using a serverless service CloudFront to solve a scaling problem.
Clever use of the right tool. Lastly, AppSync and MemoryDB. Quick recap.
AWS AppSync is a managed GraphQL service. Simplifies building data-driven apps, especially mobile web, often uses Lambda DynamoDB as backend data sources, handles real-time updates, offline sync. Amazon MemoryDB for Redis is a Redis-compatible, durable in-memory database. Ultra-fast, but also persists data unlike Elasticache Redis sometimes. Good for caching or as a primary database needing Redis speed and data structures.
Okay, fantastic overview of serverless on AWS. Let's shift to data and analytics. Querying S3 data directly. Athena?
Yep, Amazon Athena. Serverless interactive query service. Use standard SQL to query data directly in S3, CSV, JSON, Parquet, ORC. Pay per query, per TB scanned. Integrates with AWS Glue Data Catalog to understand the schema of your S3 data.
Tips for Athena performance.
Compress your data. Yeah, geez, that's snappy. Partition your data in S3, and for example, by date year, 2024 months on 4-day-28. Use columnar formats like Parquet or ORC. Use larger file sizes rather than lots of tiny ones. These reduce the amount of data Athena needs to scan, saving cost and time.
Can Athena query other data sources besides S3?
Yes, using Athena Federated Query. It uses connectors, often Lambda functions, to query data in place from sources like relational databases, RDS, NuckSQL DynamoDB, CloudWatch logs, even custom sources. Lets you join data across S3 and other systems in one SQL query.
Very powerful. What about search and log analytics? Elasticsearch.
Amazon OpenSearch Service, the successor to Amazon Elasticsearch Service. It's a managed service for deploying, operating, and scaling OpenSearch, or older Elasticsearch clusters. Used heavily for log analytics, often paired with Kibana OpenSearch dashboards, full-text search, application monitoring. Common patterns involve ingesting data from Kinesis Data Firehose, CloudWatch logs, or DynamoDB streams.
And for really big data processing, Hadoop, Spark.
Amazon EMR. Elastic MapReduce, a managed service for running big data frameworks like Apache Spark, Hadoop MapReduce, Hive, Presto, Flink, etc. on scalable clusters of EC2 instances for processing massive datasets, ETL, machine learning data prep.
What about preparing data for analytics, ETL?
AWS Glue is the fully serverless managed ETL service. You can crawl data sources, S3, RDS, etc., to discover schemas and populate the Glue data catalog. You can write Glue ETL jobs, Python or Scala Spark, to extract, clean, transform, enrich data, and load it into targets like S3, Redshift, RDS. Can convert formats, for example, CSV to Parquet. Jobs can be scheduled or triggered by events, like new data in S3.
So a typical big data pipeline might look like?
Ingest real-time data via Kinesis data streams or Firehose. Maybe use Lambda within Firehose for initial transformation. Land the raw or processed data in S3, the data lake. Use Glue to catalog it and run ETL jobs to refine it, maybe into Parquet format in another S3 location. Query the refined data using Athena or load into Redshift Data Warehouse for BI dashboards built with QuickSight. Maybe use EMR for complex batch processing jobs on the raw S3 data.
S3 as the central data lake storage. Makes sense. What's AWS Lake Formation?
Lake Formation helps simplify building, securing, and managing data lakes. It provides tools to define data sources, set up glue crawlers and ETL jobs, and crucially, manage fine-grained access, control, and governance policies for data stored in S3 through the Glue Data Catalog. Centralizes security for your data lake.
And QuickSight for dashboards.
Yes, Amazon QuickSight is the cloud-native business intelligence service. Connects to various data sources, S3 via Athena, Redshift, RDS, etc. Lets you build interactive dashboards, perform ad hoc analysis, and share insights. Has per-user pricing and a serverless option called Spice-E for in-memory caching.
Okay, what about the AML services? Quick flyby.
Sure. Higher-level AI services, recognition for image-video analysis, transcribe for speech-to-text, Poly for text-to-speech, translate for language translation, Lex for building chatbots, like Alexa, Connect for AI-powered contact centers, Comprehend for natural language processing, sentiment, entities, Textract for extracting text data from documents.
Inbuilt AI capabilities.
Exactly. Then you have services for building custom ML. Amazon SageMaker is the comprehensive platform for the entire ML lifecycle, data prep, building, training, deploying, monitoring models. Kendra provides intelligent enterprise search using ML, personalized builds recommendation engines.
Huge toolbox for AML. Okay, monitoring, auditing, performance, keeping things running well and securely. CloudWatch, CloudTrail, Config.
The big three for visibility. Amazon CloudWatch is for monitoring performance and operational health. Collects metrics from basically all AWS services, CPU, network, latency, custom app metrics. Metrics have namespaces, dimensions, timestamps, build dashboards to visualize them.
What about logs?
CloudWatch logs, central place to collect logs from EC2, need the CloudWatch agents installed. Lambda, VPC flow logs, Route 53, many others. Can search, filter logs, create metrics from log data, set alarms based on log patterns.
And CloudWatch alarms?
Trigger actions based on metric thresholds or log patterns. Actions can be send SNS notification, trigger EC2 auto-scaling, perform EC2 recovery action if instant system check fails, trigger step functions, etc. Can create composite alarms based on the state of multiple other alarms using and/or logic to reduce noise.
CloudWatch events, now EventBridge, fits here too.
Yes, it evolved from CloudWatch events. It's the serverless event bus. Reacts to events from AWS services, custom apps, SaaS partners, triggers targets like Lambda, SQS, SNS based on rules, key for automation and event-driven architectures.
Okay, CloudWatch for performance and logs. What's CloudTrail for?
Auditing. CloudTrail Records API calls made in your AWS account, who did what, when, from where. Essential for security analysis, compliance, operational troubleshooting, logs delivered to S3. Can configure trails per region or for all regions, global trail. CloudTrail Insights is an optional feature that uses ML to detect unusual API activity, spikes in provisioning, weird IAM actions, and alerts you.
So CloudTrail is the who did what log. What about what does my stuff look like right now, and is it configured correctly?
That's AWS Config. It continuously monitors and records the configuration state of your AWS resources, tracks changes over time. You define config rules, either AWS managed rules or custom Lambda rules, to check if resources comply with your desired configurations. AG, are all EBS volumes encrypted? Is MFA enabled for all IAM users?
And if a resource is non-compliant?
Config flags it. You can view compliance history. You can also configure config to trigger remediation actions, often via SNS notifications or by invoking SSM automation runbooks to try and fix the non-compliant resource automatically.
So summary. CloudWatch performance logs alarms, CloudTrail API audit trail, configuration tracking compliance, all crucial.
Absolutely. Foundational for a well-managed environment.
Let's dive deeper into security. Managing multiple accounts, AWS organizations.
Yes. AWS organizations is key for central governance. Group accounts into organizational units, OUS. Apply service control policies, SCPs, at the organization root, OU, or account level. SCPs act as guardrails. They restrict the maximum permissions available, even if IAM policies allow more. Can use block lists, deny specific service actions, or allow lists, only allow specific things. Doesn't grant permissions, only restricts.
Okay, org-level guardrails. What about finer control within IAM policies?
Conditions.
IAM conditions add context-based restrictions to policies.
Sure.
Very powerful. Can restrict based on source IP, source site, requested region, host requested region, time of day, whether MFA was used, resource tags, it's into resource tag, allows for very granular control.
Central login across multiple accounts, AWS SSO successor. AWS IAM Identity Center, used to be AWS SSO, provides a central place to manage user access to multiple AWS accounts and cloud applications, like Salesforce, Office 365. Users log in once to a portal and get access based on permission sets assigned to them. Integrates with identity sources like AWS Managed AD, external IDPs via SAML, or its own built-in identity store. Supports attribute-based access control, ABAC.
Okay, managing encryption keys, KMS.
AWS Key Management Service, KMS. Create and control cryptographic keys used to encrypt data across AWS services. Different key types. AWS managed keys used by default by many services like saa-c03, customer managed keys, CMKG control policy, rotation, can disable delete, and you can import your own key material. Also supports asymmetric keys. KMS multi-region keys allow replicating keys across regions for easier cross-region encrypted data handling. Sharing keys cross-account requires careful key policy configuration.
What about secrets? Database passwords, API keys.
AWS Secrets Manager is purpose-built for this. Securely store secrets, automatically rotate credentials for supported services like RDS, audit access, integrate with applications programmatically. AWS Systems Manager SSM parameter store can also store secrets as secure string parameters encrypted with KMS. Parameter store is more general purpose for config data and secrets, offers standard and advanced tiers with different limits features. Secrets Manager is more focused on credential lifecycle management.
SSLTLS certificates for load balancers, CloudFront.
AWS Certificate Manager, ACM, provision, manage, and deploy public and private SSL/TLS certificates for free for use with AWS services like ELB, CloudFront, API Gateway. Handles automatic renewal for public certificates. ACM Private CA lets you run your own private certificate authority if needed. Integrates smoothly with API Gateway custom domain names.
Protecting web apps from attacks like SQL injection, WAF.
AWS WAF, Web Application Firewall, Layer 7 Firewall, inspects HTTPS requests. Define rules in web ACLs to block common attacks, SQLi, XSS. Filter based on IP address, geography, request headers, body patterns. Integrates with CloudFront, ALB, API Gateway, AppSync. Use AWS managed rules, marketplace rules, or write custom rules.
What about DDoS attacks?
AWS Shield. Shield standard is free, automatically enabled, protects against common network transport layer DOT attacks. Shield Advanced is a paid service offering enhanced protection, 24/7 access to the DDoS response team, DRT, cost protection against DDoS-related spikes in usage, advanced reporting. Essential for critical apps. AWS Firewall Manager lets you centrally manage WAF rules, Shield Advanced policies across your organization. Following DDoS resiliency best practices like using CloudFront is key.
Detecting threats within my account, like compromised instances or unusual activity.
Amazon GuardDuty, Intelligent Threat Detection Service. Continuously monitors CloudTrail logs, VPC flow logs, DNS logs using ML, anomaly detection, threat intel feeds, detects things like instances communicating with no malicious IPs, port scanning, unusual API calls, potential account compromise, can optionally monitor EKS, RDS, S3, EBS, Lambda activity 2, generates findings, sends to EventBridge SNS.
What about vulnerabilities, like outdated software in EC2 or in containers?
The Amazon Inspector. Automated Vulnerability Management Service. Scans EC2 instances, needs SSM agent, and container images in ECR. Checks for software vulnerabilities, CVEs, and unintended network exposure. Provides findings with severity scores.
And finding sensitive data, PII, in S3.
Amazon Macy. Uses ML and pattern matching to discover, classify, and protect sensitive data stored in S3. Identifies buckets containing PII financial data credentials. Generates findings and alerts via EventBridge.
A very comprehensive security toolkit. Okay, let's get foundational again. Networking with VPC. Virtual private cloud.
Right. VPC lets you carve out your own logically isolated network section in AWS. You control the IP address range using CIDR notation, create subnets, configure routing, gateway, security. It spans all AZs in a region.
Key VPC components.
VPC itself. Subnets, public or private, tied to one AZ. Internet Gateway, IGW, allows communication between VPC and Internet. Router implicitly handles traffic within VPC. Route tables control where traffic goes. NAT Gateway allows private instances outbound internet access. Security groups, instance-level stateful firewall. NACLs, network access control lists, subnet-level stateless firewall. VPC peering, connect VPCs. VPC endpoints, private access to AWS services. VPC flow logs, monitor traffic.
Subnets use part of the VPC's IP range.
Yes. You define the VPC CIDR, e.g. 10.11012c, then carve out smaller CIDR blocks for each subnet, e.g. 10.1.0.0.0.024. Remember, AWS reserves 5 IPs in each subnet.
Public versus private subnet difference again.
Public subnet has a route in its route table pointing to the Internet Gateway, instances, and it can have public IPs and communicate directly with the Internet. Private subnet does not have a route to the IGW. Instances need to route through a NAT gateway located in a public subnet for outbound internet access. They aren't directly reachable from the internet.
Security groups versus NACLs, quick recap.
Security groups apply to instances. Stateful, return traffic auto allowed. Allow rules only. Default denies all. NACLs apply to subnets. Stateless, Need rules for both directions, including ephemeral ports. Allow and deny rules, processed by number order. Default NACL allows all. Custom NACLs deny all by default. Use SGs as primary firewall, NACLs as optional second layer.
How do I connect two VPCs if they have different IP ranges?
VPC peering. Create a peering connection between them. Must have non-overlapping CIDRs. Once connected, instances communicate via private IPs. Remember, peering is non-transitive. A, B, and BC doesn't mean AC.
How do I access S3 or DynamoDB privately from within my VPC without going over the internet?
VPC endpoints. Two types. Gateway endpoints for S3 and DynamoDB only, uses route table entries, generally free. Interface endpoints uses an ENI with a private IP in your subnet, supports many more services, has hourly data processing costs. Both keep traffic on the AWS private network.
VPC flow logs, what do they capture?
IP traffic metadata for interfaces in your VPC subnet ENI. Source desk, IP import, protocol, packets, bytes, *10 time action, except reject, stored in CloudWatch logs or S3. Great for troubleshooting connectivity, firewall rules, security monitoring, network analysis.
Dedicated connection from my Office data center to AWS.
AWS Direct Connect DX. Physical fiber connection into an AWS DX location. Provides dedicated bandwidth, consistent performance, potentially lower data transfer costs than Internet VPN. Connect to a virtual private gateway, VGW, attached to your VPC. Good for hybrid cloud, large data transfers.
Key VPC takeaways.
Subnets, route tables, IGW, NAT gateways, security groups, NACLs, peering endpoints, flow logs, direct connect. Understand how they work together to build secure, isolated networks.
What about network costs? Egress traffic?
Data into AWS, ingress is mostly free. Data out of AWS to the internet, egress, costs money, varies by region. Data transfer within the same AZ is usually free. Data transfer between AZs in the same region costs money. Data transfer between regions costs money. Using NAT gateway incurs costs. Try to keep traffic within AWS, use private IPs. Direct Connect might be cheaper for large on-prem transfers than Internet egress. S3 egress to Internet costs, but S3 to CloudFront is free, and CloudFront egress is often slightly cheaper than direct S3 egress.
Good cost considerations. Okay, migration and hybrid cloud, moving stuff to AWS. Databases?
AWS Database Migration Service, DMS, migrates databases easily and securely, supports homogeneous, like-to-like, and heterogeneous, different engines, migrations. Source targets can be on-prem, EC2, RDS, S3, NoSQL, handles full load plus ongoing replication, change data capture CDC. Use AWS Schema Conversion Tool, SCT, alongside for heterogeneous schema changes. Can run DMS replication instance, multi-AZ for HA during migration.
Migrating RDS MySQL to Aurora MySQL.
Can often restore an RDS snapshot directly to Aurora or create an Aurora read replica from RDS and then promote it. Simpler than full DMS sometimes.
What about migrating whole servers? Lift and shift.
Several tools. VM Import-Export brings VM images, VMDK, VHD, into EC2. AWS Application Discovery Service helps assess your on-prem servers, usage dependencies, for planning. AWS Migration Hub tracks migration progress centrally. AWS Application Migration Service, MGN, is the primary lift and shift tool now. Continuously replicates source servers, physical virtual cloud to low-cost staging area in AWS, then lets you cut over quickly to launch EC2 instances.
What if I'm heavily invested in VMware on-prem?
VMware Cloud on AWS, VMC. Run your VMware SDDC, vSphere, vSAN, and NSX on dedicated AWS bare metal hardware. Managed service provided by VMware. Extends your on-prem environment seamlessly. Use familiar tools. vCenter. Migrate workloads easily. Integrates with native AWS services too.
And moving huge amounts of data. Petabytes.
AWS Snow family again. Snow Cone, small, portable. Snowball, rugged appliance, petabyte scale. Snowmobile, shipping container truck for exabytes. Ship data physically when network isn't practical.
Okay, lots of migration support. Let's revisit solutions architecture with some more advanced patterns. Lambda, SNS, SQS combos.
Right. Using SQS queues as targets for Lambda functions provides asynchronous processing, automatic retries via visibility timeout, and durability. Add a DLQ to the SQS queue to capture messages that repeatedly fail processing in Lambda. Use FIFO SQS queues with Lambda if strict ordering or exactly once processing is needed.
The fan-out pattern again?
Publish once to SNS, deliver to multiple SQS queues, each triggering potentially different Lambda functions for parallel decoupled processing of the same event. Very scalable.
Event bridge for event-driven patterns.
Yep. Example. Log all API calls via CloudTrail. CloudTrail sends events to EventBridge. An EventBridge rule filters for specific sensitive API calls, example, security group changes, and triggers a Lambda function to send an alert via SNS.
API gateway integrating with other services besides Lambda.
Yes. API Gateway can directly integrate with many AWS services. Example, have an API endpoint that takes data and puts it directly into a Kinesis data stream without needing an intermediary Lambda function, simplifying the architecture.
Caching strategies. Where can we cache?
Multiple layers. CloudFront caches at the edge, CDN. API Gateway can cache API responses. In your application layer, use Elasticache, read as memcached, or MemoryDB for in-memory caching of data sessions. DynamoDB Accelerator, DAX, caches DynamoDB reads. Even S3 acts as a cache in some scenarios. Plus, browser caching via HTTP headers. Use caching aggressively where appropriate to improve performance and reduce backend load.
Network storage options recap. S3 versus EFS versus FSX.
S3. Object storage. Massively scalable, durable, cost-effective. Accessed via API SDK console, not a file system you mount directly, usually. EFS. Managed NFS file system. Mountable by multiple Linux instances concurrently across AZ scales automatically. Good for shared content, CMS, FSX for Windows. Managed Windows file system, SMB, FSX for Lustre. High-performance parallel file system for HPCML, often linked to S3. Choose based on access pattern, object-first file, performance needs, OS compatibility.
Automation and orchestration beyond basic scaling.
AWS Batch for managed batch job execution, running Docker containers on EC2 Spot. AWS Step functions for orchestrating multi-step workflows involving Lambda functions, other AWS services. Human tasks provide state management, error handling, visualization for complex processes. Serverless.
Infrastructure as code, CloudFormation.
AWS CloudFormation is fundamental. Define your infrastructure. VPC, EC2, RDS, IAM roles, everything, in a declarative template, JSON Yelm. CloudFormation provisions resources in the right order, handles updates, deletions. Benefits: consistency, repeatability, version control, treat info like code, automation, reuse via templates, supports most AWS resources, can create custom resources too.
What's AWS Systems Manager? SSM. Sounds like it does a lot.
It does. SSM is a unified operational management service. Key capabilities: run command, execute scripts on instances without SSH, Session Manager, secure browser-based shell CLI access without opening SSH ports or managing keys, huge security win. Patch Manager, automate OS patching, inventory, collect instance metadata. Parameter store, config secrets management. Automation, operational runbooks. Distributor, package deployment. Essential toolkit for managing fleets of instances, AWS and on-prem.
Session Manager sounds great, no SSH needed.
Correct. Uses the SSM agent, connects securely over HTTPS, logs sessions to S3 CloudWatch. Much more secure than traditional SSH access, especially via Bastion hosts. Run command is also powerful for executing scripts across many instances at once. SSM automation runbooks can automate complex tasks, triggered manually, scheduled, or by events config rules.
What about AWS Outposts? Bringing AWS on-prem.
Yes, it's a rack of AWS hardware installed in your data center. Runs a subset of AWS services, EC2, EBS S3 on Outpost, EKS, ACS, RDS locally. Managed by AWS, but you provide space, power, cooling, physical security, use cases. Low latency access to on-prem systems, local data processing, data residency requirements, hybrid cloud.
AWS Batch is designed for long-running, compute-intensive batch jobs, potentially running for hours or days, often using Docker containers, can leverage Spot instances for cost savings. Choose based on job duration, complexity, compute needs.
What's AWS Amplify for developers? Yes, Amplify is a framework and platform for building full-stack web and mobile apps on AWS, especially serverless ones. Provides front-end libraries, CLI toolchain, back-end provisioning, auth, API database hosting, CI/CD pipeline. Simplifies connecting front-end code to back-end cloud services.
And Instant Scheduler, cost saving.
It's an AWS-provided CloudFormation solution, not a standalone service. Uses Lambda and DynamoDB to automatically start-stop EC2 and RDS instances based on tags and schedules you define. Great for turning off dev test resources overnight or on weekends to save money.
Okay, we've covered so much. Any final resources? White papers, frameworks?
Definitely check out the AWS Well-Architected Framework. It outlines best practices across 6 pillars: operational excellence, security, reliability, performance efficiency, cost optimization, and sustainability. Read the white papers. Explore the AWS Architecture Center and Solutions Library for reference architectures and real-world examples.
Good pointers. And for those studying for certifications?
This overview covers core concepts across many domains: solutions architect, security, networking, etc. Review the specific exam blueprints for the certification you're targeting to focus your studies. AWS has paths for various roles and specialties.
Fantastic. This has been an incredibly comprehensive tour of AWS.
It's a vast platform, always evolving. Hopefully this provides a solid foundation for understanding the key pieces.
Well, that brings us to the end of this deep dive into Amazon Web Services. A huge thank you for sharing all that knowledge.
My pleasure. Always fun talking AWS.
And a big thank you to you, our listener, for sticking with us through this extensive exploration.
Yeah, the main takeaway really is just the sheer range of tools AWS gives you to build almost anything you can imagine in the cloud, focusing on scalability and reliability.
We hit on compute, storage, networking, databases, security, serverless containers, data analytics, MAML, a lot of ground covered.
Hopefully you can see how these pieces start to fit together and which ones might be most useful for your own projects or learning goals.
Definitely dig into the official AWS documentation and try out some hands-on labs for the services that interest you most. There's no substitute for actually using them.
And maybe a final thought to leave you with. As these cloud technologies keep racing ahead, how can understanding these foundational AWS services help you build the next generation of innovative, resilient applications? Something to think about.